In the previous program, we discussed the need to adjust system pressure to compensate for changes in ground speed. In this program, we'll discuss how to calibrate your spray system and why it is key to an effective application.
The easiest way to understand how nozzle type, orifice size, and pressure all interact to achieve the right flow rate and droplet size is to actually go through a calibration example. When we're calibrating a sprayer, we're trying to achieve the gallons per acre or gallons per 1,000 square feet that we need to get the right amount of spray solution and therefore pesticide on the target. There are three things that determine how many gallons per acre you apply. First one is the nozzle flow rate measured in gallons per minute. So for 1 minute's time, how many gallons of spray come out of that nozzle. The second thing is the ground speed at which the sprayer will be operating at. This is measured in miles per hour. The third thing is the effective sprayed width. We measure the effective sprayed width on a per nozzle basis, so it's essentially how wide an area does each nozzle have to cover. It's not the total width of the nozzle pattern, it's how wide each nozzle has to cover, and that is the nozzle spacing. So if your nozzles are 15 inches apart, their effective sprayed width is 15 inches. 20 inches apart, the effective sprayed width is 20 inches. The ground speed is based on the type of sprayer we're using and the terrain that we're going to be spraying on. So we already kind of know how fast we'll be going when we make that application. The effective sprayed width, it's the distance between the nozzles, that too is also set. So really what we're going to do is determine what flow rate do we need out of our nozzle in order to apply a determined gallons per acre at a certain speed with nozzles at a certain spacing. So we use this formula and we take the gallons per acre, multiply that by the ground speed in miles per hour, and in turn multiply that by W, the effective sprayed width in inches, and divide it by a constant, 5,940. The 5,940, it's a constant that we use to convert all the different measurement units. And that will tell us then the flow rate we need out of the nozzle in gallons per minute. So let's say we got an example here. We need to apply 15 gallons per acre. We're going to be traveling at 7 miles per hour and we make that application, and our nozzles are in 20 inches. So we multiply 15 gallons per acre times 7 miles per hour times 20 inches, divide that by 5,940, that equals 0.35 gallons per minute. So we need a flow rate out of our nozzle of 0.35 gallons per minute. Moving on to an example, we've decided to use turbo T-jet nozzle tips to make our application. We've just determined that we need a nozzle flow rate of 0.35 gallons per minute out of the nozzle. And in this example, let's say we're applying a fungicide and the label has said this will get our best results using a medium droplet spectrum. So let's look at the nozzle catalog page for the turbo T-jet nozzle. The far left column are all the orifice sizes available for this nozzle type. Each color code there represents the orifice size. So we look at the top, we have an orange, that is the TT11001. All the way to the white at the bottom, TT11008. You'll notice each one of these orifice sizes has the TT at the beginning of the name. That refers back to the nozzle type, turbo T-jet. The next three numbers, 110, refer to the nozzle fan angle. When this nozzle is operated at 40 psi, it creates a flat fan pattern that is 110 degrees wide. The last two digits represent the flow rate. If you look at that 01, put a decimal between the 0 and 1, it's 0.1. So at 40 psi, this nozzle will output 0.1 gallons per minute. We go down to the nozzle on the last part of the page, TT11008. Again, it's a turbo T-jet nozzle. It has a 110 degree fan angle. 08, we put a decimal between the 0 and 8. This nozzle produces a flow rate of 0.8 gallons per minute when operated at 40 psi. So what we would do then is we look at the next column. The next column is the pressure, the psi range for this nozzle. You notice no matter what orifice size you get, the nozzle should be operated somewhere between 15 and 90 psi. The next column is the droplet size. This shows you the droplet spectra classification when we operate that specific tip at a different pressure. It tells us the droplet spectrum created by there. And then the next two columns are the nozzle flow rate. The first column is the flow rate in gallons per minute, and the column just to its right is the flow rate in fluid ounces per minute. So remember, for our example, we need 0.35 gallons per minute. So we're going to start out in that fourth column from the right. We're going to be looking down that column for that 0.35 gallons per minute. So we're going to zoom in there on the TT11003. We notice that if we operated this nozzle at 50 psi, we would achieve a flow rate of 0.34 gallons per minute. If we operated at 60 psi, we're at 0.37 gallons per minute. So the flow rate we need, 0.35 gallons per minute, is going to be achieved at somewhere between 50 and 60 psi. And if I actually did a separate calculation, I could determine that it's going to be achieved at 54 psi. So if I operate this nozzle at 54 psi, I will achieve both that 0.35 gallon per minute nozzle flow rate as well as the medium droplet spectrum. Another concept that's very important to understand is what happens as you change speeds during the application if you're using a flow control system. As I mentioned earlier, most of the time the speed you operate the sprayer at during the application is based on the type of sprayer you're using, the terrain, and the location. How fast can you go while you're making that application? As you vary speed though, if you don't change any of the other variables, you also change your gallons per acre. When you're using a flow control system, the computer will compensate for those speed changes by changing the nozzle flow rate. So an increase in speed will result in an increase in flow rate. A decrease in speed will result in a decrease in flow rate. The system changes the flow rate by changing pressure. And that's a key point because the change in pressure doesn't just change the flow rate, it also changes the droplet size. So we're going to go through another example to highlight this. In this case, we have nozzles in 20-inch centers. They're 20 inches apart. We're applying 10 gallons per acre. And our initial sprayer speed in this example is 13 miles per hour, traveling a little bit faster. If we do that same calibration formula that we used earlier, we determine that we need a flow rate of 0.44 gallons per minute. Again, go to our nozzle catalog. We're going to stick with the Turbo T-Jet nozzle for this example. We look down that fourth column from the left. We see there the TT11004. If we operate that nozzle at 40 psi, we're putting out a flow rate of 0.4 gallons per minute. If we operate it at 50 psi, we achieve a flow rate of 0.45 gallons per minute. So the flow rate we need of 0.44 gallons per minute is somewhere in between the two. If we were to put the nozzle on there and test it with a flow meter, what we would determine would be that at 48 psi, we achieve that flow rate of 0.44 gallons per minute. At 48 psi, this nozzle creates a coarse droplet spectrum. What about increasing speed to 18 miles per hour during the application? Let's say we've got a fast sprayer, nice flat ground, good calm weather for the day. We're only going 5 miles per hour faster. Could we make this speed change? Well, W is still 20. In other words, our nozzles are still 20 inches apart, and we still want to apply 10 gallons per acre. That's what the computer's been programmed to apply. We have to redo the formula now though, and what we determine is that we need a flow rate of 0.61 gallons per minute. Now we have to have that increase in flow rate in order to maintain 10 gallons per acre at the faster speed. Well, we're not able to change our orifice size. We're still using that TT11004, and in order to make that nozzle output 0.61 gallons per minute, we would actually have to increase the pressure to 93 psi. You'll note there that 90 psi is the maximum pressure at which this nozzle should be operated. So we've exceeded that upper pressure limit. We're making a lot more small droplets. We've increased our risk of drift dramatically.